So in this video, I'm just going to go over some problems and how you solve these problems in energy and momentum. So just to remind you, in the last couple of videos, we showed that momentum wasn't normally conserved under the Galilean transformation, so we had to adjust it a little bit so that it was conserved under the Lorentz transformation. So what we did is momentum is now defined as mu over the square root of 1 minus u squared over c squared. And now momentum is conserved. And we also, since momentum is conserved, we came down here and we got kinetic energy and the total energy, which was the kinetic plus mc squared. And you'll notice if I just take this mc squared onto that side, then this is the total energy. Now, we said there's no such thing as potential energy in relativity. All we have are these two types of energy. You have your energy due to your mass, and you have your energy due to your motion. There's no gravitational, electrical potential. There's no potentials. And this is conserved too. So we have two things that are conserved, and those are the two things that we want to use, right? Now, I'm going to just real quick derive a simple a nice, useful formula that connects these two together. And it makes problem solving a lot easier. You notice if we were to take the E that we have over there, and square it. If we square this term right here, that's m squared c to the fourth all over 1 minus u squared over c squared. 1 minus u squared over c squared. And now let's take the momentum and square that also. If we square the momentum, it's m squared u squared. I'm not going to worry about the vector nature of it since we're squaring it. U squared, m squared u squared all over 1 minus u squared all over c squared. And suppose I were to take this term and multiply it by c squared. Both sides. So if we multiply this side by c squared and this side by c squared, and now just subtract these two. So we got e squared minus p squared c squared. Well, that would be this minus this. Well, if we factor out, we have the common denominator, 1 minus u squared over c squared. And if I factor out the m squared c squared, then what's left? Well, up here, if I pull down an m squared c squared, there's still a c squared minus, and since we pulled out the c squared, we're just left with a u squared. Okay, and now if I pull out another c squared, I'll make this c squared over c squared and pull out another c squared. We end up with m squared c to the fourth. This would be 1 minus u squared over c squared, but I have a 1 minus u squared over c squared. That's all gone. That's it right there. It's just e squared minus p squared c squared is just m squared c to the fourth, or e squared equals this plus this. It's so useful. It's one of our most useful equations. I'm going to write it down right here. E squared is equal to p squared c squared plus m squared c to the fourth. Why? Since this is something that's conserved and that's something that's conserved, makes this problems a lot easier. Okay, so now we have that formula. You'll be using it a lot. Okay, so now what I did was I said, let's go ahead and solve some problems. So what I did is I took the problems, you remember this textbook, this Survey book, I took the problems from that, Xeroxed them off, and I moved them up to Canvas. If you go into the Canvas, go into Files, you'll see there's 3 pages there about homework problems. I think it's problem page 1, 2, and 3. And I have those pages here. And now I can just pick certain problems out of that book and just work them out. I would print out those pages yourself, and then I don't want to write the question out. I just want to, I'll read the question, but I'm not going to write them all out. And so this first one I'm going to do is problem number 8. They say a proton moves at a speed of 0.95 c. 0.95 c. And they say calculate, first of all, its rest energy and its total energy and its kinetic energy. So when they say calculate its rest energy, they just mean mc squared, m of the proton c squared. Now, we know what the mass of the proton, one of the perks of getting the textbook right here is if you open up the book, most books do that, they give you the mass of the proton right there. And then you noticed right there, it's 938 MeV. I don't want to say per c squared. So they already gave me the answer. This is 938 MeV. So I just had to grab it from, remember they were looking at the mass and they said per c squared. I'm going to interchange it and forget about that because that's usually what people do is they just say the mass is the same as the energy. Okay, so that's 938 right there. So that was the first part, pretty easy. And then they said, what is the total energy? Well, the total energy is E. Now I could either get it from this, or I could get it from this, or I could get it from, well, we'll get it from, or I could get it from this right here. There's the total energy right there. Remember, energy, you can either write it like that or like this. So it's mc squared, so E, m of the proton, c squared, all over the square root of 1 minus u squared over c squared. We know what the numerator is. It's 938 MeV. They gave me the speed. It'd be the square root of 1 minus 0.95. The c's would drop out, 0.95 squared. So it's just that number. Now, if you plug in that number, it's about 3, this is about 3.2. Remember, this is a number bigger than 1. So it's 938 times 3.2, and this is around 3004 MeV. Remember, the units of energy were in EVs, but MeV means millions of EV. Okay, so that, and then they also asked for the kinetic energy. What's the kinetic energy? Well, we can come right here. We know the kinetic plus the rest mass is the total energy. So the kinetic, or we can write it from there, there's the total energy minus the rest mass energy. So the kinetic is the total energy, which is the 3004 MeV, minus the rest energy, 938 MeV. Okay, which is like about 21, what did I get? 2066 MeV. Okay. So there's the kinetic, the total energy, and the rest mass energy of that particle. Okay. Well, let's look at another one. Number 9. Number 9 here. It says an electron has a kinetic energy. So now we've got an electron. And they say the kinetic energy is equal to is 5 times its rest energy. Well, its rest energy is mass of the electron c squared, and it's 5 times that. Okay. So that's what they gave us right here. They want its total energy and its speed. Well, first of all, to get the total energy, since they gave me the kinetic and we know the rest mass, I guess the total energy, we'll just plug it right into here. E is equal to the kinetic, which is 5 times m sub e c squared plus the rest mass, m sub e c squared So E is just 6 times m sub E c squared. And so again, the inside cover of the book gives you the mass of the electron too. If we look at the mass of the electron, it's right there. It's 0.511 MeV. So this is 6 times, I'm just going to go 0.5. I'm not going to worry about the 1 right here. 0.5 MeV, which is 3 MeV. So the energy would be slightly more, but that's okay. 3 MeV. So there's the total energy right there. They ask anything else? They ask, and its speed. They ask its speed right here. Well, where's the speed come in? We know that the total energy is given by this, so we can calculate the speed right here. So we're going to set the total energy, which is the 3 keV, equal to mc squared all over the square root of 1 minus u squared over c squared. Well, we know this was a half right here. Half an MeV is the mass of the electron. If we bring this down below, 3 divided by a half is 6. So we got 6 equals 1 all over the square root of 1 minus u squared over c squared. If we square both sides, we get 36 equals 1 all over 1 minus u squared over c squared. We'll flip both sides, so 1 over 36 equals 1 minus u squared over c squared. Or swap these two, so u squared over c squared is equal to 1 minus 136, which is 36, or u equals, we can get that, u is equal to, take the c over there and take the square root, so it's the square root of 36c. And if you plug in the number for that, it's 0.986c. Okay, again, we're just using these formulas over and over again. Here, if we go down to number 11. A proton in a high-energy accelerator is given an energy of, they say 50 GeV. They say 50 GeV. Well, GeV is billion, so if I put it in terms of MeV, we'll just move it to MeV. That would be 50,000 MeV, just because that's what we've been working in all along right here. So this is a proton right here. Again, we know what the mass of the proton is right here. So that's its kinetic energy. So this is the kinetic energy. They want us to get the momentum. Well, now they want us to find P right here. Well, might be easiest since they give me, well, there's a P right there. I could either use this formula or I have to use this. But if I get this, I have to get the speed. And they did not tell me what the speed is. I'd have to solve for it. So let's just come down here and get this one right here. So if we wanted to, what we first need to get is, they gave us the kinetic. We need to first get E. But we can get E from right here. And then we'll just plug it in. So E, first of all, is equal to the kinetic plus the mass of the proton c squared. Well, the kinetic is 50,000 MeV. And then the mass of the proton, didn't we already say it was right here? 938. Plus 938. So this is all in MeV. So there's the energy. The total energy is 50,938 MeV. So there's the total energy, and now we can just go ahead and plug it into here. If I want to solve for P, I'm going to move this term over to that side. So E squared, so P squared C squared equals E squared minus m squared c to the fourth. Well, let me plug in and get that number over there. So p squared c squared equals E squared. Well, that's this number squared. 50,938 squared minus mc squared squared. So that's 938 squared. Hopefully I did that right there. And that is 50,000. Well, it's, and then take the square root of both sides. If I take the square root of both sides, it's gone, and it goes over to here. I did that. PC is equal to 50,930. 930, and that would be, remember, this is an energy, so that would be MeV. And then if I wanted to get the momentum, just divide out the C, but they usually just leave it as a C. So P, I'll just write it right here, P is just 50,930, 50,930 MeV per C. Okay, so there is the momentum. Okay, this is number 11. The momentum and the speed. Now they want the speed right here. Well, now they have the, if I want to get the speed, I could either plug it into here since I know the momentum, or I could plug it into here since I know the energy. I like this spot better because there's only one U in that. Here there's two U's and it'd be a little harder to solve right here. So we'll just get it from right here. So we got E, which we said was 50,938. So we're going to plug it into E equals mc squared all over the square root of 1 minus u squared over c squared. So E was 50,938 equals mc squared, which we already said was the 938, all over the square root of 1 minus u squared over c squared. Okay, we can bring that down below and divide that. If you take this number and you bring it down over here, that number becomes 54. That is, this over this is 54. So 54 equals 1 over the square root of 1 minus u squared over c squared. We can square both sides and flip it. The square of this is 2,948, and then flip it. So we got 1 over 2,948 equals 1 minus u squared over c squared. It's u squared. We could bring this term over, take that back. 1 minus this is, so we get u squared over c squared is equal to 1 minus this, which is 2,947 over 2,948, very close to 1. And then move the c over and take the square root. And in that case, u, it's pretty fast, u is equal to 0.9998c. Pretty close to the speed of light, but I guess it'd have to be to get you up to 50 GeV for a proton.